I know I have a lot of video resources that are already out there for this course, right? Each lecture represents an individual skill, and there's videos that are out there that are intended to um, be a supplement to what you already get in terms of lecture content. A lot of it is going to be a repeat of it, but it's an opportunity for you to reinforce your understanding on sort of that one specific item. From time to time, I'm going to put together what I'm going to call 30,000-foot view videos. They might get into some details of some skills that we've talked about, but in general, they're going to be videos that bridge multiple skills, sort of allowing you to see the connection between different skills. And in particular, in this second learning unit that we have in Gen Chem 2, it's a large learning unit. There's lots of individual pieces that sort of come together with that. So I want to take a second and just remind you of what that overview is, and then give you a few slides here that are going to allow you to see sort of that big picture and the connectedness between things that might seem a little bit unrelated. So to start here, just highlighting here are the topics that we cover in the second learning unit. Again, it's a pretty large one. There's 10 overall skills that we sort of have here. And what we're doing is we basically learned about the atom in our first learning unit. And then we're saying, you know what, when we make molecules or substances or compounds, it's because we're combining those atoms together and we're learning how that happens. So look at sort of the organization that we have here. We can have atoms trading electrons to form ionic compounds. We can have atoms sharing electrons to form covalent compounds. And when we form covalent compounds, wow, we've spent a lot of time learning about the shapes that those molecules can be, from very simple Lewis structures to complex biological molecules, right? We've spent a good bit of time talking about how we draw Lewis structures, how we think about molecular shape and polarity, and then even building on that to understand how the electrons within atoms are going to overlap those electrons within their overlapping orbitals to generate those molecules, okay? Our first quiz is going to be sort of on that content, which is a boatload of content to begin with. But then we expand even further and say, let's think about how the electrons are arranged in molecules, right? We had atomic orbital theory where we knew the quantum numbers to sort of describe where electrons lived. Now we're going to say, let's think about where those molecules live once we have electrons get shared between atoms to make a molecule. Okay, that's molecular orbital theory. And then we're going to have a couple of skills where we learn how to draw some of those more complex molecules. We're going to learn how to draw what we call line structures or skeletal structures, and then learn how organizations of different atoms in defined groups create what we call functional groups. And just like the periodic table is organized, where if things live in the same column of the periodic table, they have similar chemical and physical properties as atoms. When we talk about those atoms combining in a certain way to form certain groups of atoms that we call functional groups, we also understand that those molecules have similar chemical and physical properties. So again, this is the 30,000-foot view of this second learning unit that hopefully is going to allow you to see some details for these processes. I already have a video out there that sort of talks about these skills. How do we take and think about combining atoms together to make covalent compounds, recognizing that we have to have a certain amount of glue that will connect those atoms together, and then thinking about how that dictates the shape of the molecules, the polarity of the molecules, and being able to describe things like hybridization. So there's a video out there already on that. But I wanted to put a video together that sort of summarizes some of this early content that we've talked about. Just, when we think about the energetics of some of these processes of forming ionic compounds and covalent compounds. So I'm going to have 3 videos that I'm going to go through here. The first one actually has nothing to do with chemistry. These are all ones that we did in class, but it might be a nice review for you and also see the interconnectedness of these videos. So the first thing that I sort of talked about to introduce the energetics of chemical processes is we talked about your bank account. right? And this gets us to think about when we want to know the overall energetics of a process, we need to think about the things that are costs in that process and then the things that are gains in that process. So we're going to think about those same things here in terms of things that increase our bank account or decrease our bank account. And we're going to look at that, for example, over time. Let's say over the course of a month, okay? And what we're going to see here is that there are going to be things that are going to increase our bank account. And I'm going to highlight those in red here. And I know my analogy might fall a little bit here because you might be like, red seems like it's a bad thing, like it's a cost. But I want to use these same colors to sort of connect with what we're going to see with chemistry systems. So we're going to use anything that's in red, something is going to increase sort of our system here. And in this case, the system is our bank account. And then we're going to use green to map out anything that decreases sort of our bank account. And so what we're going to have here, let's imagine at the start of the month. So at the start of the month, our bank account is here. Okay, so on our y-axis, if you will, we're thinking about sort of increases or decreases here. We're having money. What's the value of our bank account, either higher or lower, okay? And then we're progressing through time, right? And so we're imagining at the start of the month, we end up here. So let's imagine some things that happen early on, sort of with what happens here. Maybe you deposit a paycheck. So that's going to increase your bank account. Maybe grandma gives you some birthday money. So you've got birthday money that's going to add to your bank account. So again, we're highlighting that these are things that are increases to what we're measuring on our y-axis, which is the value of our bank account. We're increasing in energy. And then let's maybe say there's a few things that happen later on in the month that we're going to have our rent that's going to decrease, take up some money. That's going to be something that decreases our bank account. And I'm not saying that my arrows are to scale here, but maybe you have to buy some groceries. And then maybe you have some movies that you go to. And again, I'm not saying that my arrows are to scale here, but what I want to highlight is there are some things that are going to decrease your bank account. Okay. Now, what we're going to have here is if we were to sort of look at a movie of how our bank account changes over time, what we're going to see is we're going to be increasing and then eventually decreasing. Okay. Such that at the end of the month, we're going to end up here. Okay. So this is going to be the start of the month. This is going to be the end of the month. And truly, at the end of the month, if I look at where my bank account started at the start of the month and I looked at where it ended up at the end of the month, it honestly doesn't matter if these processes happened in this order. It doesn't matter if my paycheck is first, then I have birthday money, and then I have all of these bills that I have to pay. Where those sort of come into, adding to or subtracting from my bank account, what you might be interested in at the end of the day is really just asking the question, what is the net? What is the change in the amount of money? Okay, we're going to call that what is the net in your bank account at the end of the month. And again, if you're just looking start of the month to the end of the month, the goal with your bank account is not that you have less money at the end of the month than you had at the start of the month, because if the same increases and decreases to your bank account happen in the next month, you're going to continually be decreasing your bank account. Okay, the main thing that I want to sort of highlight here is if you want to figure out what's the net of your bank account at the end of the month. So again, the net of my bank account at the end of the month is really a sum of things that added to my bank account. Okay, we're going to call those our increases, and the things that decreased my bank account. So we've got decreases to our bank account. Now, conceptually, I want you to think about this. Every one of these things in our bank account has an absolute value. Maybe your paycheck is $250 and then birthday money is $50. But rent might be $300, groceries might be $50, and movies might be $25, right? If I want to have this net, I need to manually sort of account for the sign of what those absolute values do to my bank account. Paychecks are going to be things that are going to be positives, and things that I subtract from my bank account, even though there's a monetary value associated with it in my bank account, I have to subtract things like rent and groceries and movies. I need to add paycheck and birthday. And if you've balanced your checkbook, right, you know that you have to do this. When you're adding in your paycheck or your birthday money, you write plus and you add that in. When you're subtracting out the check you wrote for groceries, or the the check that you wrote for rent, or the debit card that you used for groceries or movies, you have to subtract that from your bank account. Again, the idea is that the net is really the sum of things that add to and subtract from your bank account, but you may need to, in your check register and when you're balancing your bank account, manually recognize that things need to have a positive sign or a negative sign. And I hope I didn't make that too confusing by just sort of giving a bank analogy, okay? But what we're going to do now is we're going to look at two examples of chemical systems that are related to this philosophy. I'm going to talk about the formation of an ionic compound and then the formation of a covalent compound. Okay, we're going to see things that look similar. All right, and I know this picture can look really scary, but I don't want it to be. Here's what I'm going to highlight, some important things that we're going to talk about with this. The first thing is I want to make sure to highlight what these terms mean on sort of the title of this slide. Delta HF. And if we haven't gotten to this, or you haven't heard this yet in lecture, I sort of want to define what it is. Delta HF. So delta H is a way to measure energy. H is enthalpy. It's a way to measure sort of bond breaking or making in chemical processes. So when we talk about delta HF, here's what I want you to remember what delta HF is. It allows us to think about an equation. So it is the formation of 1 mole of a substance from its elements. Okay, so let's look at the process that we have here. We're talking about making lithium fluoride. So see if this makes sense here, okay? I'm going to write this equation up top here. If I want to make lithium fluoride, you need to know that lithium is a +1 cation, fluoride is a -1 anion. So I'm going to be making this salt, and I want to make 1 mole of it, and I want to make it from its elements, how I find them in their elemental form. Well, that's going to be lithium as a solid metal. Right, that's how we find lithium. Hopefully you know how you find fluorine in its elemental form. It's found as a diatomic gas. So it's going to be F2 gas. Now this is a super important part here. I know we're used to balancing equations and not having numbers that aren't whole numbers, but for here, because I need to have 1 mole over on this side, I'm going to put 1/2 over here. Okay, because my fluorines come 2 at a time as a diatomic gas, that's why I have to have a 1 there. We're going to see more of this later, so I want you to think about what it means to have a delta HF equation and subsequent value. Okay, so delta HF here is the formation of 1 mole of a substance from its elements, and if we're looking at forming lithium fluoride, that's an ionic compound. Okay, here's the equation that we draw. Okay, so a couple of key pieces here that I want to highlight as I walk you through this video, or this picture here. You do not need to know the math of what's going on here, okay? I want you to connect it to what we talked about with our bank account, okay? We're going to have things that are costs, take us uphill, things that are gains, things that are take us downhill. But specifically for this problem, we have already learned about all of these different steps. I want you to know definitionally what they are, and I'm going to walk you through that in just a second here. But I want to highlight, anytime we see an up arrow is going to be a cost, okay? Keeping with our sort of system with our bank account, anything that we saw going uphill, we labeled red, okay? So look at all of these orange arrows here that I'm going to highlight are arrows that are going uphill. Okay, anything that we're going to have as a gain is something that goes downhill. Okay? So look at this. We've got a yellow or an orange arrow that goes downhill, another orange arrow that goes downhill. Remember when we were doing this analogy here? Here was our net. Okay? So this is our net reaction. This is going to be our delta HF. This is going to be the sums of our costs and our gains for this overall process, and that is going to be delta HF. So delta HF here is going to be what we have in blue, and it's the sum of all of our costs and our gains. Okay, so you do not need to know you're not going to have a math problem that you have to do with this, but here's some concepts that I want you to be able to think about. I want you to be able to think about what a delta HF equation is and sort of what the energy of it is. The energy of this process is the sum of our costs and our gains, okay? Now, another piece that I want you to think about is a big picture concept, and this is why I'm doing this 30,000 foot view and then having 3 examples here. Bank account, we're going to think about ionic compounds, and then our next slide is going to think about covalent compounds, okay? I want you to remember that chemistry often happens for things to go downhill. So chemistry happens to go downhill. Okay? I don't have a lot of space to write on this slide. So chemistry happens to go downhill. The net of our reaction, the sum of our costs and our gains. If we want something to be favorable, I want my gains to outweigh my costs. That means the net sum of all of them is going to be an arrow that goes downhill. Okay, we're going to expand on this again in a learning unit later in the semester when we think more about a process called thermodynamics, which is a way of thinking about the energetics of chemical processes. But we're sort of introducing it now with this concept of lattice energy. Okay, the last thing before I sort of take a deep dive on the details of this picture, because I do want you to be able to identify the chemical processes that are happening with our costs and our gains. I just want you to know them by name here. But I want to define one more piece on this slide. I want to define lattice energy, okay? I've got it defined down here, okay? We define lattice energy. Lattice energy is actually going to be the opposite of this arrow. This arrow goes downhill. That's energy that's a gain. We define lattice energy as the energy or the enthalpy change associated with taking a crystalline solid, that's an ionic compound, and separating those ions into the gas phase. Now that doesn't sound like something natural, right? You don't take and shake some salt out of your salt shaker. That's sodium chloride. That's a crystalline solid. You don't put it on your stove and then all of a sudden like you make sodium cations in the gas phase and chloride anions in the gas phase. That's not what happens. That doesn't seem natural, right? That seems like it would require a tremendous amount of energy to do that. Said another way, if we think about if we had those ions in the gas phase and they found one another, wow, they would want to hang out with one another and be that crystalline solid. So it is a huge downhill slide if we had those ions in the gas phase. So this is actually going to be the opposite of lattice energy. So what I'm going to do here on this slide is I am going to walk you through all of these arrows. There's 5 arrows that we have here, 3 uphill and then 2 downhill arrows. So 5 arrows total. I want you to know what's happening by name and be able to think about whether that's a cost or a gain. I'm going to give you a preview. A lot of this we learned in Learning Unit 1. They're names of things that we already talked about. Okay, so we've got pictures to sort of go along with what we're talking about. So we're going to start right here, and we're going to start with the things that we talked about. If we want to build lithium fluoride, we have to take lithium metal and fluorine gas. Okay, now what has to happen for those two to end up as crystalline lithium fluoride? Let's walk through this picture here. So I'm going to talk about it in 3 ways. I'm going to talk about for each of these arrows and each of these places. I'm going to say, what are we starting with? Let's look at what it looks like on a molecular level or an atomic level. And then we're going to ask, what are we doing? And I'm going to define it with sort of a term that you're going to need to know. Okay, this is a term that you'll need to be able to think about. So let's look at, we're taking lithium solid and then fluorine gas. Look at what changes here as we go uphill. Well, I didn't change anything here, right? So I'm going to highlight in orange and then we're going to label it. And this is what you need to know. You need to know sort of this term, this definition. Look at what happened here. I took solid lithium and I made it into lithium as a gas. Look at my picture here. Here's solid lithium, like lithium's a solid. All of those atoms are kind of hanging out together. And now I separate them and I put them in the gas phase. So what do you need to know from this? Well, that doesn't sound like it's a process that would give me energy. It sounds like it takes energy, okay? And we're going to define all of these pieces. This is the atomization of lithium. That's what's happening at this step. Okay, if I were to draw sort of a simple equation for what's happening, it's lithium solid going to lithium as a cation in the gas. I'm sorry, lithium, not as a cation, I'm sorry. It goes, not a cation yet, it goes to be lithium, oops, too big of an eraser there. It goes to be lithium in the gas phase, okay? So I want you to be able to think about the steps that it takes to take a solid metal, mix it with a gas, and make a salt. Okay. And again, just like we talked about with our bank account, it doesn't really matter which order we think about these in for some things. Okay. But conceptually, it'll make sense to think about this in a certain order. I take my hunk of lithium solid and I make it into gaseous lithium atoms. Okay. No change yet with fluorine. Name of this is atomization. Here's what happens. Okay. So let's look at what's changing now. Okay. Now, I still have lithium in my gas phase. When I go on to my next step, I'm just changing one thing at a time. So that's going from this picture now to this picture. Now what I'm going to be doing is I'm going to be changing my fluorine here. So I took fluorine, that was 2 fluorine atoms that were hooked together, and I broke the bond between them. Hopefully you can think about, and hopefully you had a little bit of Lewis structure drawing last semester, right? Here's what fluorine gas looks like, F2. I need to break that fluorine-fluorine bond. So I'm going to take 2 fluorine atoms that are hooked together, and I'm going to generate fluorine atoms. Now notice, look at this. Remember I started out with a 1/2 mole of this? So it's going to make 1 fluorine atom, okay? So I've got a whole bunch of diatomic fluorine, and I make it into atomic fluorine, okay? Fluorine atoms is a gas. Now I've got each of my atoms that I want to build my ionic compound with as gaseous atoms. Now, remember what an ionic compound is. Ionic compounds are generated when things trade electrons. So what we're going to have happen is we're going to have our lithium atom lose an electron, and then we're going to have a fluorine atom gain an electron. That's the trading of electrons that happens with ionic compounds, right? So, but I'm going to show this as 2 separate steps. Okay, so let's put a name with this. We said we were going to break this bond. Okay, so when we have this bond that gets broken, we're going to have bond energy that gets broken. Okay, so bond energy. So bond energy is what we need to sort of pay the cost of. It was atomization was the cost of the first step. Then it was we have to break a bond. So we've got bond energy that we need to break. And now we've got one little more uphill space that we have to go. Huge arrow that we have here. Let's look at the next step that sort of happens here. We're going to have, now look at the things that change. I'm connecting these together. Here's what happens. We've got lithium in the gas phase. That's going to make lithium cations in the gas phase. And that happens because I lose an electron. Okay? This is ionization. And last learning unit, we learned about ionization energy. This is ionization energy 1. It is the loss of the first electron in a lithium cation to generate a lithium atom to generate a lithium cation. Okay, so that's what we have there. We learned ionization energies are always going to be costs. Okay, we studied and we talked about trends in ionization energy. That was sort of a skill from our first learning unit. All right, now we start getting to the gains. Where do we get money back from this process? Well, there's two arrows that are downhill, okay? This is where we're going to have our fluorine atom gain that electron that lithium atoms gave up and become a fluoride anion. So again, connecting our pieces together, look at what's changing here. We're going to have our fluorine atom become a fluoride anion. And here's again what happens here. We're going to have a fluorine atom gaining an electron and become a fluoride anion, still in the gas phase. Still in the gas phase, okay? That is going to be electron affinity. We learned that last learning unit too, right? We abbreviated that EA. And even though we didn't talk about trends in electron affinity because it was not always super trendy, we didn't have things that always followed a same pattern, we learned about what it was. And one of the things that we talked about is it is almost always going to be downhill. It is almost always favorable for an atom to gain an electron. It is always unfavorable for an atom to lose an electron. So now we're starting to sum up our costs and our gains. And if I stopped at this process, this is the energetic point that I'd end up with, and I would have gone uphill in energy. So the last piece, which we've already talked about, is super important. Now we are going to have these two atoms that have become ions in the gas phase. So I'm going to have fluoride as an anion in the gas phase and lithium that is in a cation in the gas phase. They are going to say we would much rather be lithium fluoride as a solid. And when they find one another, the energy that gets given off from that is intense. Huge arrow. But note here, if I add up my costs and I consider my gains, the net of this process overall is favorable. Now, maybe you might remember, if not, I'll show you in just a second. There was a video that we showed when we had not lithium fluoride reacting. We actually had the electronegative boogie of atoms reacting. We had fluorine with cesium, and that explosive process was generated a tremendous amount of heat and light. And that's because this blue arrow was huge downhill process for those two elements to react. So I wanted to switch over now and show you that chemical reaction of fluorine with cesium, like the electronegativity boogie of reacting the most electronegative and the least electronegative atom on the periodic table. I'm not going to show the whole video. We watched this in class. Of course, we have to get through. Oh, you can even see this. People kind of fast forward here to the most reactive part. Okay.
Yeah, looks good. Right, are we nearly ready? I'll lower this. Yep.
So again, they've got that super reactive metal and then that gas that they're gonna, whoop, and there we go, there it is. I think they'll show it sort of zoomed in here.
Incredibly beautiful reaction there between cesium and fluorine, this intense light. And I don't think many people have seen that before.
So huge reaction. Remember, the things that are happening there is we're atomizing our metal, we're taking our fluorine gas and we're splitting it up into fluorine atoms, and then they're trading their electrons, and then those ions in the gas phase are finding each other and they're forming solid lithium chloride. That's sort of that powder that you see forming there. So really neat, just highlighting what an incredibly reactive reaction that is, what a huge downhill slide that is in terms of the overall energy of that process. Wow. I know this video is getting on the long side. I'm going to encourage you when you watch it, maybe stop and start it so that you can see these processes, right? But what we're going to go on to now is look at the same kind of a thing, but think about it for covalent compounds. So pause for a second if you need to sort of take a break before we move on to thinking about covalent compounds, but you're going to see something different. We want to talk about the costs and the gains to determine the overall energy of a process, right? The costs and the gains to determine the overall energy of forming an ionic compound. Last one again is going to be the costs and the gains for determining the overall energy for forming a covalent molecule. All right, so here's what we're going to have for this guy. Now, I want to highlight, this is a reaction that should be familiar for you. This is how you're going to heat your furnace in the winter. This is methane, so let's write down what these species are. This is CH4, so this is methane. We're going to react methane with oxygen gas, and we're going to generate carbon dioxide and water. This is something that I want you to know. This kind of equation is called a combustion equation. So I want you to know what a combustion equation is. A combustion equation is going to take a fuel, it's going to combine it with oxygen, and it's going to generate carbon dioxide, water, and energy. Okay? This is the key of this process, right? This is going to be a downhill process. It's going to generate energy for us. Okay, so I want you to know what a combustion reaction is. This happens to be a combustion reaction with the fuel methane, which is what you find in your furnace. Now, note here, I'm going to add a few coefficients in here because this is a balanced chemical equation. I need to have 2 molecules of oxygen, okay, and I'm going to generate 2 molecules of water here. So if I consider this as a balanced chemical equation, I'm going to have CH4 plus 2O2 generates CO2 plus 2 H2O. And we're doing this in our furnace, so all of these are going to be gaseous molecules. So like we saw before when we did our bank account or we did our lattice energy problem where we talked about forming an ionic compound by trading electrons, if we want to think about what is sort of the downhill energy for this process, note we also call this a delta H. This is going to be the delta H for this reaction. What is the net of this? We're going to consider our costs and our gains. So again, these are going to be our costs. Those are going to be things that go uphill in energy. And then we're going to consider our gains. So our gains are going to be things that go downhill in energy. So here's where this becomes a little bit different and a little bit more hypothetical with this burning of methane in our furnace here than it was when we considered lattice energy for example, lithium fluoride. This is not the reality of what happens in your furnace. This is what we call an empirical or calculation-based method to figure out sort of what our overall process is worth. So here's how this happens, right? Just like we've learned to build molecules with our model kits, or we learned how to do it in ChemDraw or even in virtual reality, what I want you to imagine is that these are sort of Lego pieces. These atoms are Lego pieces that get glued together to make methane and oxygen. And if I want to make new molecules like carbon dioxide and water, I need to disassemble my Lego pieces or disassemble those molecular models that I made. And so what we're going to do is we're going to think about disconnecting all of our bonds and creating individual atoms. That is going to be a cost. Hopefully you can envision this. Like if I were to break apart every single bond in these molecules, that would be a cost, right? And that's an important thing because then when we build bonds, when we put atoms together and we allow their electrons to live between those atoms as covalent bonds, that's going to be a gain. Okay, so this is a conceptual exercise, but it has to do with thinking about bond energies. Okay, so what we're going to do, and I'll show you how we do this, is we need to add up any bonds that are broken. Those are going to be costs. You'll notice here that it's going to have a positive value that we associated with it. Do you remember when we did our bank account analogy and we said, you know what, whether we consider the value of grandma's birthday money or the value of going to the movies, there's a numerical value that's associated with it, but the sign to what it does to your bank account was something you had to manually select. Grandma's birthday money adds to your bank account. Movies subtract from your bank account. The same is going to be true here. When we disassemble molecules, that's always going to be a cost. We're putting a positive sign with it. When we rebuild molecules and we form bonds, that's always going to be something that we add a negative sign to. So again, that's going to be a negative sign. And then to figure out what the overall process is, so again, that's our blue piece here. Our overall process is going to be our costs. let's see, I want to say equals, hang on one second. I want to say our overall process is going to be equal to, let me move this down here, our costs plus our gains. And here's why I like adding things together. The order of operations doesn't matter. If you're adding A and B, it's the same as adding B plus A. The same is not true for subtracting because you can get the sign wrong. A minus B is not the same as B minus A. So this is why I do it this way, so that we always make sure that the sign is right. We need to manually understand that anything that is a cost, I give a positive value to. Anything that is a gain, I give a negative sign to. I add up my costs and my gains, and then the overall process is going to have a positive or a negative delta H with it. This is where you need to remember chemistry happens so that things go downhill. Downhill means I'm going to have a negative delta H. So when I go downhill, downhill is going to be equal to a negative delta H. And that means that process happens easily. I get energy out when that process happens. We highlighted for a combustion reaction, energy is given out. All right, I told you that for sort of the lattice energy and this whole process, you were not going to see something where you had to do any math with that, at least not yet, okay? You do need to think about math for a problem like this. And I want to remind you where we calculate and figure out our costs and our gains is this magic table that we call table 9.2. Now, on a quiz or something like that, rather than giving you the entirety of this table, I might just give you the relevant pieces. But on an exam, you're going to be getting this table. You need to know how and where to look things up and then what you do with those numbers. And I want to point out a couple of important things. So for this table, you need to find the bonds that you're breaking or forming. You'll notice that everything on this table has a positive value associated with it. So if you are breaking that bond, that's a cost, you're going to keep it as a positive value. But if it's a bond that you're making, you need to change the sign. The net overall for your process is your costs plus your gains. So keeping my color coding system here, anything that is breaking it, that's a cost. Okay, we're going to make that value positive. If we're making it, it's a gain. That's going to be negative. The overall process, right, is we're summing up all of our costs and our gains. And again, here's the piece that I highlighted. If that net value is positive, that's an uphill reaction. Energy would be needed to be added. For our example that we just did, it's a downhill process. Energy is given off in that process. Okay, last little thing here is I just want to show you, this is a problem that is a worked through in class problem. There's problems like this that are assigned for homework. I want you to sort of look at this and you're going to see a problem like this. Now, early on, I'm likely to give you the structures of these molecules, right? Because I want you to be able to see what the species are so that you can identify the bonds that you either need to be thinking about breaking or forming, okay? When it comes time for the test, okay, you're likely to have to draw these molecules because that's a skill that's important, right? We learn in this learning unit how to draw molecules. So you need to know what that molecule is so that you can figure out what bonds you're breaking or forming. So just sort of giving you a preview of where this is going. One other piece that I want to make sure to highlight is something like carbon dioxide or oxygen. I'm going to zoom in here. Look here. If you have a carbon doubly bonded to an oxygen in any other molecule, this is your magic number that you're going to use. But if you have specifically carbon dioxide, look here at the structure of carbon dioxide, right? Here's carbon dioxide. Carbon doubly bonded to oxygen on one side, doubly bonded to an oxygen on another side. That's a special sort of arrangement of carbon doubly bonded to oxygen. It has a special value, 799. And note that if you have carbon dioxide, you have to use two of those because there are two of those bonds. Okay. If you're forgetting or wondering if you, oh, well, like what? Look at this. This is just a little bit higher. Okay. So if I have, and let me just draw this on here so we can see this. If I have carbon dioxide, okay, and I'm talking about making carbon dioxide, I need to use double that value. Make sure you don't get tripped up on that. Note here that they also put oxygen specifically in there. Again, oxygen, here's the Lewis structure of oxygen. These are things that you should know how to draw, but if you see oxygen, you are breaking that oxygen-oxygen double bond that's specific to oxygen. Everything else, and it's put in alphabetical order, you are looking up what bond you might have, whether it's carbon-hydrogen, carbon-carbon. Note here that there are carbon-carbon double bonds, carbon-carbon triple bonds, right? That's all organized. You need to know how to use this table, and importantly, know whether you're using these values for this table as a positive value because you're breaking those bonds, or a negative value because you're making those bonds. Wow, I know this was a really long video, but hopefully you've been able to watch it in a little bit of pieces, and it's allowing you to sort of see that 30,000 foot view, thinking about the energetics of processes. Chemistry happens so that we go downhill in energy, and the overall energy for a process is really just the sum of all of our costs and our gains.